Okay, so as we have derived the variance, we can now state the mean ergodicity theorem for White's stationary processes. We say that a White's stationary random process x of t is mean ergodic if the limit of this expression, which is the variance of the time average, okay, goes to zero. The limit t goes to infinity as 1 over 2t, the integral from minus 2t up to 2t, 1 minus absolute value of u divided by 2t, multiplied by the covariance evaluated at u. If this goes to zero, okay, as t goes to infinity, then yes, your time average will converge to the true value of the mean. And in this case, we say that the limit as t goes to infinity, which defines the length of the observation period, the time average converges to the true mean. Okay, this is ergodicity in mean. Next, we can look at ergodicity in autocorrelation, and as I have stated earlier, this is a little bit complicated than ergodicity in the mean. First of all, let's define the time average to estimate the autocorrelation. As we know, the autocorrelation by definition is equal to the mean of x of t times x of t plus tau. And I can just write it in this way because I know that x is White's stationary. And therefore, I define the time average for autocorrelation in this way. Okay, I observe this process from minus t up to t, and then I multiply x of t within this interval with x of t plus tau. Okay, integrate this product from minus t up to t and divide by my interval length, which is 2t, and that is my time average for estimating autocorrelation. Of course, to have this time average converge to the true autocorrelation for a specific value of tau, of course, we have to have an ergodic theorem. And for this purpose, you see this product, we will define this product as a new random process, W of t, defined as x of t times x of t plus tau. Okay, and this shows us that if this newly defined random process W of t, if that is mean ergodic, then x is going to be ergodic in autocorrelation. Okay, because the mean of WT corresponds to the autocorrelation of x of t. Simple as that. Therefore, I'm going to use the ergodic theorem, mean ergodic theorem for the White's stationary random processes, and I will apply that to WT. Okay, so for x of t to be ergodic in autocorrelation, that means W of t should be mean ergodic, in which case it should satisfy this, the limit as t goes to infinity, 1 over 2t, the integral from minus 2t up to 2t, 1 minus absolute value of u divided by 2t times the autocovariance of w evaluated at u should go to 0. But of course here, the autocovariance of w here is by definition the autocorrelation of w minus the product of the mean values of w at t and t plus u, right? That is the definition. Okay, then if you just plug in the definition of autocorrelation, you have this is the expected value of w t times w t plus u, assuming that w itself is White's stationary. Then just plug in these definitions. This is the definitions here: x of t plus tau, and then wt plus u will be x of t plus u times x of t plus tau plus u. You see, I have 4 terms here inside the expectation, and of course I have minus the autocorrelation of x squared, because each of these, the mean of the expected value of w, is going to be equal to the autocorrelation of x. So I have the square of autocorrelation. Now this is the general condition here. If this here, right, if this is satisfied where the autocovariance of W is this expression, okay, if you put this in, this integral, compute it, and then if you can show that it goes to 0 when t goes to infinity, only then you can say that, yes, the time average I have defined here will really go to the autocorrelation of x, okay? Now, one observation here, x of t, well, we assumed it to be White-Sands stationary, but that is not sufficient for ergodicity in autocorrelation. X of t here, as you observe from this expression, will have to be fourth order stationary, okay? So as I said, if the order of the statistics get higher, then proving ergodicity gets more complicated.